So since we know that the voltage produced in a generator is in the AC form, so now we discuss on AC. AC stands for alternating current, right? And the AC current or the AC voltage could be represented by the expression of V equal to V naught sine omega t, and the current for AC will be I equal to I naught sine omega t, where omega is called as angular frequency, and it can be related to frequency of f, where omega equal to 2 pi f, right? And this V naught here is stand for the maximum value of voltage, and the I naught here is stand for the maximum value for current. So what is the relation between the maximum value and the RMS value? So V RMS is equal to V maximum divided by square root of 2, and however I RMS is equal to I maximum divided by root 2. So I'm using the naught to represent the maximum value. So root mean square, RMS stand for root mean square, right? Root mean square value, for example, for the voltage is the readings or is the value that you got it from multimeter. Okay, so this is AC expression for voltage and current. Okay, now let's look at what happens if we connect a resistor to an AC source, resistor with the resistance of R. So you can see that we can apply Ohm's law for AC as well. So Ohm's law said that V equal to IR. So in this case here, the V will be RMS. The I is RMS as well. We could also state V in terms of the maximum, where V naught is equal to I naught multiplied with the R. That's Ohm's law. And when you use the oscilloscope to measure what is the voltage across the resistor, and also the current flow in this pure resistive circuits, you found that V, the voltage across the resistor, and the current are in phase, right? There's no phase difference between the current and voltage across the resistor. Okay, now let's look at another circuit where we call it as a pure capacitive circuit, where you connect a capacitor to an AC source. Right? So in this case here, we can also apply Ohm's law, where V equal to IR. But in this case, R, we don't use R anymore, but we are using a term called it as reactance. Right? This reactance is called it as capacitive reactance, okay, which is an opposition of current, and it has the unit of ohm. Right? It has a unit of ohm. So if the V here is referred to RMS, then here will be RMS. This one will be RMS as well. Okay, after you apply Ohm's law, and this capacitive reactance here, XC, is varies inversely proportional to the frequency, where Xc is equal to 2 pi Fc. C is the capacitance. So what is the F here? F is the frequency of the generator. Right? This one is called as a generator or the voltage source. Okay. Then the phase difference between the voltage across the capacitor and the current flow through in this pure capacitive circuit is not in phase, but the I is leading, or I leads BC by 90 degrees. Right? There's a phase difference between the current and also the voltage across the capacitor. Okay, now let's look at an inductor connect to an AC source with the frequency of F, inductor with the inductance of L. For example, the voltage here across the inductor is VL. So in this case, the voltage across the inductor and the current is not in phase as well, where I lags the voltage across the inductor by 90 degrees. Right? So of course, we still can apply Ohm's law. V RMS is equal to I RMS multiplied with the inductive reactance. So inductive reactance, XL is stand for inductive reactance, okay, which has a unit of ohm as well, where XL is proportional to the frequency. Right? XL is equal to 2 pi FL. So the frequency, of course, is referred to the frequency of the generator. And now, if I combine these three circuits together to form a series circuit, right? So I combine the three components, R, C, and L, connect together and connect in series, connect to an AC source. So what happened to here is you can see the phase difference, right? Between the voltage across the resistor, voltage across the capacitor, voltage across the inductor compared with the current. So we use a diagram called it as phasor diagram to represent the phase difference of VL, VC, or VR. Right? So phasor diagram. So this phasor diagram will be something like this. This is, let's say, the length of the arrow is representing the maximum value of the voltage across the resistor, and the current will be in the same component, same direction, because they are in phase. So this is the maximum current, and the voltage across the inductor is here because the voltage across the inductor is leading the I by 90 degree, or I is lags the voltage across the inductor by 90 degree. And however, the voltage across the capacitor will be here, right? Because the current is leading the voltage across the capacitor by 90 degrees. So this is a phasor diagram for RLC series circuit. This circuit we call it as RLC or RCL series circuit, right? So now we can simplify the circuit to make it as, redraw it as this. This is VR0. Here is VL0 minus VC0, right? So we just combine these two vertical components to make it as one component of VL0 minus VC0. And we have the resultant V0, right? This V0 is actually the voltage, maximum voltage of the AC source. Maximum voltage of the AC source of V0, right? That's a maximum value. So here is the maximum value for the AC V0. Okay. And here we have one term, also additional term, call it as phase angle of phi, right? This is a phase angle of phi. Phase angle exists between the angle between this phase angle exists between V0 and also VR0, right? And it is called it as phase angle. Okay, now if you refer to this phasor diagram, it can be stated that the voltage across voltage of the generator, maximum voltage of the generator V0 is equal to VR0 square plus VL0 minus VC0 square root of it, right? So again, this knot here represent maximum value, right? Knot here represent maximum value. Okay, so this is a maximum value. Okay, now we can explore to apply Ohm's law into this expression. V equal to IR. Therefore, here will be I naught R, I naught square, R square, plus I naught XL minus XC square, right? And square root of it. And then factor the I naught. You will get I naught here, square root of R square, plus XL minus XC square. Okay, then you can write the equation as V naught equal to I naught multiplied with Z, where Z is called it as impedance. Alright, so Z is equal to this. This is Z. Okay, so Z we call it as impedance. It's actually the effective resistance, but we don't call it a resistance, so we have a special name for it, call it as impedance, right? So it has the same meaning as effective resistance, okay, where the unit is still as ohm, right? So we can, this actually is Ohm's law, right? V naught equal to I naught multiply with a Z, or you can write it as in terms of root mean square value, where V RMS is equal to I RMS multiplied with Z. So this is expression for the AC, okay, if you relate to the voltage of the generator. Okay, so Z here is the impedance. Okay, now, so we already know what is the voltage, right? We discussed on the voltage, we discussed on voltage of the generator, voltage of the across the resistor, voltage across the inductor and the capacitor. So now let's move on to another term, call it as power. Okay, call it as power. So this is the AC. Further explore it. Let's look at power in the AC circuit. Okay, what is power? Power defined as the product of VI. Okay, now we refer to AC, so this power here is called it as average power delivered to the AC circuit is equal to V RMS multiplied with I RMS, right? But because we are looking at the RLC series circuit, and the phase angle between the VR, VC, and VL will be different, so we have additional term for the power. Okay, we call it as cos phi, and this cos phi here is called it as power factor, right? Power factor, and power here is only dissipated. Dissipated means loss in resistor, and therefore average power loss is only equal to I square RMS multiplied with R. Even we are referring to the RLC or RCL series circuit. Okay, so for RCL series circuit, the power loss is due to the power loss through the resistor only. Okay, what happened to the power loss in capacitor and inductor? So because the capacitor and inductor is basically a device used to store energy. So basically there's no energy loss in capacitor and also inductor. Alright, and therefore power is only lost in resistor. And how can we get the power, the power factor expression, right? How we can find out what is the value of the power factor. So power factor is equal to cos phi. And this power factor, if we refer back to the phasor diagram, here is the phasor diagram. So cos means adjacent divided by hypotenuse, means power factor will be V R naught divided by V naught, right? Power factor will be V R naught divided by V naught. So power factor V R naught divided by V naught. So what is V R naught? V R naught, if we apply Ohm's law, V R naught will be I naught multiplied with R, and V naught here is the V maximum value of the generator, which is here, maximum value of the generator. So the V naught is I naught multiplied with impedance. Okay, then can cancel off. So eventually, power factor is equal to the ratio of R to Z. Okay, so this is power factor. Right? And there's one special conditions called it as resonance, right? Resonance. So we can also find out what is the resonance. So resonance is a phenomenon where the RLC circuit is oscillate. Then at this resonance, the IRMS in the circuit is maximum. Okay, so when IRMS is maximum, if I refer to Ohm's law, V equal to IR, so IRMS is equal to VRMS divided by the impedance, right? So in order for you to get the IRMS as maximum value, you have to get the impedance as minimum, right? So what is minimum? What is impedance? So just now we have derived that impedance is this. Impedance is R squared plus XL minus XC squared and square root of it, right? So if you are using this expression of the impedance, you refer back to the how we get the Z minimum, right? So the impedance, in order for you to get the Z minimum impedance, Z minimum, right? So means Z is a square root of R squared plus XL minus XC squared. So to get the minimum of Z means XL is equal to XC. Right, XL is equal to XC because R cannot be 0. So the only thing for you to get the minimum of impedance is this terms is equal to 0. So how to get this term 0? XL is equal to XC. So which means for resonance, right, in order to have a resonance to occur, condition is XL must be equal to XC. Right, so what is XL? XL is 2 pi FL. So at this frequency is called it as resonant frequency. So I put it as F naught. And for capacitive reactance is inversely proportional to the frequency where XC is equal to 1 over 2 pi FC. So the frequency here is F naught. And therefore, I can derive out the resonance frequency expression where F naught is equal to 1 over 2 pi square root of LC. So this is resonance. Resonance in RC circuit. So resonance only occur in AC circuit, right?